Hi students, today we're going to talk about 5.7b, where we will learn about proofs with parallelograms. So first, let's review some of the properties and some of the ways we can actually prove parallelogram. Here they are. We are going to focus on the right side. We can use converse of opposite sides are parallel, and we can also use converse of opposite sides are congruent. We use opposite angles are congruent, and we can also use diagonals bisect each other. And the last one I emphasized before, one pair of sides are congruent and parallel. And also don't forget the definition. The definition says two pairs of parallel lines. And also we have talked about rhombus, rectangle, and square. Here are ways to prove them. For rhombus, the definition, all sides are congruent, or the diagonals are perpendicular. Or you can say each diagonal bisect a pair of angles, so being an angle bisector. That's for rhombus. For rectangle, we can prove they're all right angles. Also, we can prove the diagonals are congruent, and this is the special case for that one. And that last square, ways to prove, we can use the definition, all sides are congruent and all angles are right angle. Or you can say it's a rhombus and it's a rectangle, so we can use these things to actually prove them. And that can also work to actually prove a shape, a quadrilateral is actually a square. Now let's get into some practice thinking. First examples. You're going to think, what theorem can you use to show that the quadrilateral is a parallelogram? So first, let's have a look. Number one. In this case, we can see, these two angles are being labeled as the same right here, and these two are the same. So we're going to use converse of opposite angles are congruent. Unfortunately, these theorems do not have the name, so you do actually need to write down the statements. The next, number two. As you can see, is not opposite angles, it's actually right here. The converse of opposite sides are congruent. That's number two. And number three, we can see it's being bisected right here. So that is converse of diagonals bisect each other. And these are actually the few things we can use. We can have a look again. Right here, bisect each other, sides congruent, sides parallel, right there. Now let's practice something more. Describe how to prove that ABCD is a parallelogram. You're not writing the whole proof, but you are trying to think through. So you see this, we can see, there's a parallel, there's a side right here, the angles right here, they also share that side. So clearly we can actually do side, angle, side to prove the triangles are actually congruent. Then we can show these two sides are congruent as well. Then we can have two pairs. So converse of opposite sides are congruent. And that is how we can prove it. And next, number 5. You can see these two angles are the same, these two angles are the same, they share this line. So this time it's angle, side, angle. And with that, we'd actually prove lines are parallel because we so we basically have, it's two different ways. One, we can use angle, side, angle, or we can use alternate. Interior angles, converse of that. Because these two lines we can prove they're parallel, these two lines we can prove they're parallel, then voila, we can actually do that. So next, number 6, we can see these two angles are the same, and they're also the same, so at least we know AD is parallel to BC, that's for sure. If they are parallel, we can actually prove this angle right here is same side interior angle, so that is at the 180 degree angle, the same side interior angle, and this is also same side interior angle. We can prove they're the same, and then we can use the opposite angle. So converse of opposite angle. I'm running out of space, so I'm just gonna leave there. We're gonna say all converse of opposite angles are congruent. So that's number 6. Next, a few examples. A student claims incorrectly that the marked information can be used to show that the figure is a parallelogram. Draw a quadrilateral with the marked properties that is clearly not a parallelogram. So this is just asking to draw a quadrilateral to show, for example, number 1, to show the these two angles are the same, these two angles are the same, and the quadrilateral we draw is actually not a parallelogram. So for example, I can just do 2 random lines. And because they're vertical angles, of course they're going to be the same. And you can tell that is not a parallelogram. But it still satisfies these two being the same and these two being the same because they're just vertical angles. So number 7. Next, number 8. If we actually want to show these 3 sides are the same, I can just make 2 sides that are the same first. As for this third one, I can even just let it tilt, say that way. Then this is the shape we actually end up with. That's clearly not a parallelogram. We can say these 2 sides or 3 sides are the same. Next, number 9. 2 lines are parallel and the other lines are actually the same. So I'm just gonna, use the same length like right here. That is 8. And clearly this shape I just draw, that is not a parallelogram. That's number 9. Next, we got some real proofs. Number 10. Angle A and angle B are congruent. Angle A and angle C are congruent. Angle B and angle D are congruent. We're proving parallelogram. So this time, we're going to use something that we haven't exactly encountered. So the first one, this is something that is kind of guaranteed because a quadrilateral is basically 2 triangles. Each triangle is 180 degrees. That's why all the interior is 360 degrees. That's the interior angle of quadrilateral. So after we set that up, we're going to put them all together. So we have 2x and 2y. That is going to be substitute property. We're just going to put them together. And next, we're going to take out the 2. So that is actually the opposite of distribution, but it's still distribution property. Next, divide both sides by the 2. Divide both sides by the 2. We got x plus y equals 180. And our x are a and c, our y's are b and d. So now we can actually replace them back. A and B are together 180 degrees, A and D are 180 degrees, which in other words, they are supplementary. That's the supplementary definition. Next, after we say they're actually supplementary, we can know they are parallel. So that is going to be converse of same side interior angle theorem. After we show that, we know they're parallel, all parallel. So that is going to be converse of the opposite sides are congruent. That's how we can prove it is a parallelogram. That's example 10. Example 11. We already know it's a parallelogram. This time we're trying to prove AB and CD are the same. And we're also trying to prove EC and DA are the same. So if they are parallelogram, the definition tells us they're all parallel lines. So parallel lines. Next, 1 and 4. If we know they're parallel line, 1 and 4 looks like alternate interior angle. So by that theorem, we know 1 and 4 are congruent, and 2 and 3 are congruent. And we also know AC is the shared line right there, so that's reflexive property. And because of this, we have angle, side, angle to prove 2 triangles are congruent. After that, we can know AB is congruent with CD, and BC is congruent with DA. So that's the last thing, CPCTC. That's example 11. Next, example 12. Same thing, we already know it's a parallelogram. We're trying to prove they actually bisect each other at E. So basically proving these two are the same and these two are the same. If you have a look, that basically are 2 triangles that are congruent. So that's kind of how we're going to prove it. First, since it's a parallelogram, we know these 2 sides are parallel. That's by the parallelogram definition. Next, alternate interior angle, we can see that 1 and 4 are congruent, 2 and 3 are congruent. And so now we have 2 angles that are congruent, which means we just need another side. So if we know AB is congruent with CD, which is why that is going to be called opposite sides of parallelogram are congruent. After that, we know angle, side, angle. We know two triangles are congruent now, angle, side, angle. And then that tells us the AE and CE are congruent, BE and DE are congruent. Because of that, that is CP, CT, CE. After that, we can say you can see AE, CE, DE. That means E is actually the midpoint for both diagonals. So that is the definition of bisector or midpoint, either one. Next, example 13. We know lines are parallel and also congruent. We're trying to prove is a parallelogram. If they're parallel, you can kind of tell these two are the same. And if they're actually the same, we have something about triangles we can use. So let's have a look. After it's given, we know SQR, which this angle I just labeled, is congruent with QSP. And that is by, since they're alternate interior angle, so alternate interior angle theorem. Next, QS. This is the line they both share right there. So that is reflexive property. But after that, we have angle, side. We actually have side, angle, side. So that means they are congruent. That is by side, angle, side congruence. After that, for sure now it's actually going to be something about angles. Now we can actually prove that QSR, which is this angle, is the same as this angle. So now we can actually use that to prove the other two lines are parallel. So right here, these two lines are parallel. That is converse of alternate interior angle theorem. Lastly, because they are parallel, we also know this parallel. So these two together can jump to the conclusion that is a parallelogram. So converse of opposite sides are parallel. And that is the last example for 5.7b. Thank you.